EDEXCEL A-Level Maths Mechanics 2021. Let's get it. Okay, first off, I can see constant acceleration. Fantastic, it means we can use SUVATs. So let's start writing down what we know. We know the acceleration is, and I like to use my vectors as columns. And we also know that t equals 0, so that's initial velocity. So that's u, so u equals 4, 0. And it says find the velocity at t equals 2. So I know t equals 2, and I'm looking for the velocity. So which is the SUVAT that does not have s? Well, that is v equals u plus at. So v is equal to u, which is 4, 0, plus a, which is 2 minus 3, multiplied by t, which is 2. So reading across, I get 4 plus 2 times 2 is 8, and I get 0 plus 3 minus 3 times 2, which is minus 6. And of course, you could write that as 8i minus 6j if you so wish. Next, it says this is the starting point. All right, we'll use that in a minute, and find the vector or the position vector at t equals 3. So let's see how far it's moved in 3 seconds then. So s is equal to ut plus a half at squared. So u is 4, 0 and t is 3, plus a half of a is 2 minus 3 and t is 3, so times that by 9 because it's t squared. Reading across, 12 plus 9 is 21. 0 plus half of negative 27 is minus 13.5. Now that's how far it's travelled in 3 seconds, but it started at 1, 1. So it's gone 1, 1 plus this displacement is moved. So therefore it is a total position or final position of 22 minus 12.5. Pulleys. Oh, I love these questions. I love them so much that you just want to skim read all this stuff here. Rough plane, yeah, bloody. That means there's friction. The angle's quite important, I'll give you that. Coefficient of friction is a 6th, yeah, that's important. Stone A is released from rest and moves down the plane. That's pretty important as well. Write an equation for A. Yeah, let's just get to it, shall we? So let's first off draw a diagram and put in here alpha, and there was a blob here of 3m, and it went over here, down here, and that was m. And we were told that tan alpha equaled 3 over 4, so I draw a little triangle like this, and I put alpha in here. This would be 3, this would be 3 because it's the opposite, that would be 4 because it's the adjacent. 3, 4, 5 triangle because of Pythagoras, so that tells me that cosine alpha is the adjacent over the hypotenuse and sine alpha is the opposite over the hypotenuse. Right, very useful. Now we get to forces. Draw that straight down there. 3mg, that's the weight. Draw that straight down there. mg, that's the weight of that one. Now this one we're going to take components. So I'm going to draw a line down there. That angle is always the same as the slope. And that's the cosine because it's next to the angle. So it's 3mg cosine alpha. You come in this way and you are opposite the angle. So you are 3mg sine alpha. Right, next force we need is the reactional force, which is always perpendicular to the floor or the slope or whatever. And we were told that it was rough, this slope, so therefore we're going to get some friction. We're also told that the object was going to be moving down the slope, so it's going to be accelerating in that direction. And in fact, the whole system is going to be accelerating like this, and that's important to put on. So the friction is always going against the motion. So friction is going to come this way against the acceleration. And finally, we're going to have tension in both parts of the string, and they always face each other just like that. Great, that's all the forces. That's a beautiful force diagram. And now we're going to do an equation of motion for A. So the sum of the forces equals mass times acceleration. What are the forces going in the direction of acceleration? There's only one, and it's this one. That's going parallel to the slope, and it's going down the slope. So it's 3m cos alpha. And what did we say cos alpha was? We said it was 4/5. Great. Next, oh, sorry, whoopsie, sine alpha, which is 3/5. And we've also got friction going the wrong way and tension going the wrong way. And that's going to equal the mass multiplied by the acceleration. There's our equation of motion for A. That's part A of this question. Part B is to work out the acceleration in general. Okay, so let's do an equation of motion for B. So I'm going to have, yes, here, tension going up in the direction of motion minus mg going down, and that's going to equal the mass multiplied by the acceleration. Right, once I've got both equations of motion, I just add the two together, and that's going to cancel out the t's, because we've got one positive, one negative. And how many mg's am I going to have? Well, I've got 9/5 here, take away 1. So 9/5 take away 1 is 4/5. So I've got 4/5 mg. And I've still got this minus f, which is actually a bit annoying. We'll sort that out later. And that's equal to 4ma. Okay, so I need to sort this f out. F, as we know, is mu times by r. Mu in the question I was told was a sixth. And r is going to equal exactly 3m cosine of alpha. And cosine of alpha being 4/5. Now, how do I know that? Well, the only force on A perpendicular to the slope is R and this 3mg cosine alpha. So they must be equal to each other, because it must be balanced, because the object is not accelerating off of the slope. So I can sub that in. So now, well, let's just actually simplify this down a little bit. So that's a half times 4/5, so that's 2/5 mg. So I'm going to get 4/5 mg minus 2/5 mg equals 4ma. So that's 2/5 mg equals 4ma. The m's will cancel nice and neatly. Divide through by 4, and I'm going to get a is equal to 2/5 divided by 4 is 1/10 g, which is what they've asked for. They then asked for us to sketch a velocity time graph of B from the moment that it is released, and then explain why. Well, B is just going to shoot up, and it's going to have constant acceleration. So it's just going to be a constant acceleration graph, which is just going to be a straight line. Velocity time, and you can say that this is linear as constant acceleration. And then finally, it's asking us to say that in reality the string is not light. State how this would affect your working in part B. Well, if the string had weight, then it would have weight like this, and therefore the tension would be needed to keep it up, otherwise it would go slack. So the tension would point up like this, like that, in order to balance out. So you can say that the tensions would be different to each other. In fact, they'll be different to each other. Sorry, to each other. It's terrible writing here, because it's going to have a, it's going to be like this, isn't it, the object. So that tension and that tension will be different. We have weight there, so one of them will have to counteract the other one. A question on ladders. This is a really classic question, but students do find this very difficult. So what I'm going to do first is label some of the forces. And I know the mass of the rod is M. It's going to act at the center of the rod, and the weight will be mg. I also know there will be a reaction force from the ground pushing the ladder up. Those are the horizontal forces, and I know that there is going to be, sorry, those are the vertical forces. I know there are going to be some horizontal forces. Let's call this one N for the normal reaction. And I also know that this ladder is wanting to slip down this way. So friction is stopping it from slipping down. So friction is going to be acting this way, keeping it in equilibrium, keeping it in place. So from these two bits of information, if I look at the verticals, I know they must be balanced, so R equals mg. And if I look at the horizontals, I know they must be balanced as well, so N equals F. I also know that the frictional force is at least, it's less than or equal to mu multiplied by the reactional force. That's one of those, that's an equation that you have to know for mechanics. And next, what I'm going to want to do is take moments at A to try and eliminate some of these forces down here and get an equation for N and whatnot. So in order to take moments at A, I will need the perpendicular forces. So the distance from A to the weight is little a, but I'll need to multiply that by the perpendicular force. So the perpendicular force will be a component of the weight, and that will be mg cosine theta. And you can use angle rules to check that that theta is the same as that theta, because for example that's a right angle triangle there, and that will be 90 minus theta, so therefore the other side of that angle will be theta. And I'm also going to want to take components of this force here. Now this will be n sine theta. The way I can prove that is theta will be the same as this. And then if I was to draw a right angle triangle here, this angle will also be theta, and theta is now looking opposite that component, so therefore it's the sine component. Okay, right, I've got my components, so now I can do my moments. So I know that the clockwise moment is going to be little a multiplied by the force, and the anti-clockwise moment is going to be 2a multiplied by the force n sine theta. So now what I can do is I can rearrange for n, which will give me a mg cos theta over 2a sine theta, and that will equal n. And I know n will equal f from my horizontal components, and I know f will be less than or equal to mu r. So simplifying down, I can cancel the a's here. I'll have a 1/2 mg, cos over sine is cot, and that will be less than or equal to mu r, and mu and r we know is mg from our first equation we wrote in the top right. So dividing through, I will get 1/2 cot theta is less than or equal to mu, which is as required in the question. Okay, the next part of the question gives us some more information. It tells us what the theta value is, it tells us what the mu value is, and it says that there's now a horizontal force kmg which is applied to the beam, and it acts towards the wall, and it is now in limiting equilibrium. So lots to take in there. Let's explain what that means. So there's now a new force that's come in and it's pushing against the wall, and that's kmg. Now that it's pushing against the wall, in fact, the ladder, or is pushing towards the wall, the ladder now wants to slip forward. So friction is going to counteract that and try and keep it where it is, and it's going to push it in this direction. And the frictional force will be at its maximum in order to keep it in position. So it will equal mu r, which means it will equal a half mg, because we know that mu is a half from that bit of information. Yes, good. Okay, now what we can do is we can look at our taking moments at A again. So now if I take moments at A, I will have once again AMG cos theta is equal to 2AN sine theta. So N will equal, once again, it will be AMG cos theta over 2A sine theta, and that will simplify down just like it did before to mg cot theta, a half. Now that's the value for n, and what we now know about our horizontal components is that, let me just get rid of some of this working over here to give me some space. We know that n is equal to, n plus, so the ones going to the left are n plus a half mg, and that's equal to the ones going to the right, which is kmg. And we know that n is a half mg times by cot theta, and we know that tan theta is 5 over 4, so cot is the reciprocal of that, so it's 4 over 5. So this would be times by 4 over 5 plus a half mg equals kmg. We could divide each term by mg. A half times by 4/5 is 2/5, plus a half itself is, well, it's just a half. That's equal to k, so therefore k is equal to 0.9. And I think we are done, or is there a question at the end? No, that's it, perfect. Okay, projectiles question. All the information is on the diagram apart from these two main points here. And the first question asks us to find the time taken for the stone to travel back to the ground, essentially. So I'm going to look in the y direction, the vertical direction, and I'm going to set up SUVAT, S, U, V, A, and T. I want my distance to travel is minus 70. I want to go back down 70 from the start position to where I want to end up. Now the initial velocity, well, I've got 65 here, and I'm going to have to stop, I've put it into components. So because the vertical is opposite the angle, this is going to be 65 sine alpha. So that's going to be 65 sine alpha. And we also know the acceleration due to gravity is minus 10. It's always going downwards, gravity is always pulling you down. And t is what we're trying to find. So we're going to use the one which does not contain v, and that is s equals ut plus a half at squared. So let's go grab some space down here. And I will write that s equals ut plus a half at squared. I've got minus 70 u was 65 sine alpha t, and I've got a half of minus 10, which is minus 5 t squared. Now, what is that 65 sine alpha? Well, I was told that tan of alpha was 5 over 12, so I can set up a triangle like this. By Pythagoras, that will be 13. So the sine is the opposite over the hypotenuse, so it's 5 over 13. So if I rearrange this, I'm going to get 5t squared on that side minus 65 times 5 over 13 is 25. So 25t and then minus 7t equals 0. I'm going to divide through that by 5 to get this. And then I'm going to solve that to get t minus 7 t plus 2, and t must therefore equal 7 because it can't be negative. So 7 seconds. Now it says find the speed of the stone at the instant just before it hits the ground. Well, once again, if I set up my my y components, I've got s is equal to minus 70. I've got u is equal to, it was 65 sine alpha. The velocity is now what I'm looking for, and I have a is equal to minus 10, and I have t is equal to 7. So I can use any one actually, and I'll use the most straightforward one, which is v equals u plus at. So the velocity is equal to 65 sine, which we said before was 65 times 5 over 13, which was 25. A was minus 10, and times that by t, which is 7. So the velocity here will give you minus 45. So that's the velocity in the y direction. Now I also need to work out the velocity in the x direction. Now for the x direction, something we need to remember is that the acceleration in the x direction is always equal to 0, and that means that the speed doesn't change in the x direction. So what is the speed in the x direction? Well, if we go back to our triangle at the start, the initial velocity in the x direction will be 65 cosine alpha, and cosine alpha will be 12 over 13. So the velocity in that direction will be 65 times 12 over 13, which will be 60. So the overall speed will be the magnitude of the velocity. So it'll be going 60 along that way, and it will be going minus 45 down that way. So the speed will be this magnitude here. So that will be the square root of 60 squared plus minus 45 squared. So I'll put that into my calculator, and I'll do the square root of 60 squared plus 45 squared, essentially. That's going to be 75. So 75 meters per second. Okay, the next question asks me one limitation other than air resistors. Oh no, air resistors is the standard one, but they're cutting you out from that one. Well, the assumption is that the stone is modelled as a particle, so that's a big assumption. That doesn't account for the stone's dimensions. So you can say the assumption that the stone is modelled, terrible spelling, sorry, as a particle, and doesn't account for dimension, or possibly that the object is spinning. Okay, so this is a variable acceleration question. So you need to know that in order to move between the formulas for displacement, velocity and acceleration, you can differentiate down or you can integrate up. So at the moment I have velocity and I've been asked to work out acceleration, so I'm going to differentiate down. So if I wanted to work out the acceleration, that's the derivative of the velocity with respect to time. And this will give me, and I'm going to write it as a column because I prefer to write them as columns. So I'm going to do the i's first, and that's going to give me 3 over 2 t to the minus a half. And the t's, that's going to give me just minus 2. And it wants to know the acceleration. Oh, that's it. Done. That's the acceleration. And then it says find a value for t the instant when p is moving in this direction here. Okay, so part B. So we want the velocity to be something of something similar to x minus x, because the two components of velocity have the same magnitude. They both have 1, but the I component is negative. So it's essentially moving in this direction. So 1 across, 1 down, 45-degree angle down in that direction. So my velocity is equal to 3t to the half over minus 2t. So combining these two equations, hopefully you can see that the bottom one is the same as x equals 2t. So therefore 3t to the half is equal to x and 2t is equal to x. So these two must be the same in order for our equation to work. If I divide through by t to the half, I will get this. If I divide through by 2, and then if I square both sides, I will get 9 over 4 is equal to t. Okay, I've now been asked to work out the position, and I've given an initial condition, or sorry, just a condition, which we'll use in order to work out the constant which is created when we integrate, because we're going from velocity up to position now, or displacement. So I will need to integrate. So I'm going to integrate that velocity function, which was 3t to the half and minus 2t. Still going to keep it as columns, I just prefer using columns. And that is going to be with respect to t. So that will give us the position r. And when I integrate, I up the power by 1 to get 3 over 2, and then I divide. I do 3 divided by 3 over 2, which is 1.5, and I'm going to get just 2. So it's going to be 2t to the 3 over 2 on top, and on bottom, that's going to up the power to a square term, divide 3, I'm going to get minus t squared. But I'm going to get plus c, as we always do when we integrate. But because I'm in vector form, I'm going to put ci here and cj there. And now what I'm going to do is I'm going to use my my condition, and that's when t is 1, r is minus j. So when, let's do it over here, when t equals 1, r is equal to minus j, so 0 minus 1, essentially. So subbing in, I get r is 0 minus 1. When t is 1, this gives me 2. And when t is 1, it gives me minus 1 here, plus ci cj. So that tells me that ci cj is equal to minus 2 on the top line, because 0 is equal to 2 minus 2. And cj must be 0. So I can now write my my overall position as 2t to the 3 over 2 minus t squared minus 2, and there's no constant term on the j direction. So that's my position. Okay, next question. Find the exact distance of p the instant when p is moving with speed 10. Okay, speed 10. Well, the speed is the magnitude of the velocity. So the speed is equal to the square root of the two velocity components squared added together. So that tells me that 10 is equal to the square root of, and vi is the velocity in the I direction, which is given right at the start. It's 3t to the half. And vj is minus 2t. So that is 3t to the half squared, and vj is was minus 2t. Squaring both sides and then multiplying out these square brackets is going to give me 9t, and this is going to give me plus 4t squared. So great, that's a quadratic which I can solve. That's going to give me minus 100. I'm going to be lazy and just go to the quadratic solver. Though I probably should be able to factorize that. Well, I could definitely factorize that, but I'm just being lazy. Minus 100. And we get 4. And a negative, but t must obviously be positive because it's time. But I don't think we're quite done yet. That tells us the time when the speed is at that, but it's asking me for the exact distance. So I'm going to have to use my position formula, which is right here. Perfect. So I just need to sub into that. So 2 lots of 4 to the 3 over 2 minus 2. And here I've got minus 4 squared. So this is going to give me 2, 8, 16. 16 minus 2 is 14. And this is going to give me minus 16. But I don't think we're quite done yet. That's the position, but it's asking for the distance. And the distance is the modulus of the displacement components. So I'm going to get 14 squared plus 16 squared essentially, or minus 16 squared, but the same thing. And I will go to my calculator for that. And I will go to the square root of 14 squared plus 16 squared to get an exact value of 2 root 113. Thank you very much for watching. I'd appreciate it if you would like and subscribe and share with any friends who are also doing A-level maths. Thank you.